So have you ever wondered what's the difference between a low mass star versus a high mass star? Let's talk about it. So my name is Chris. Welcome to the Cosmos. Let's get started. So, like all stars, they all eventually form out of a nebula of dust and gas. And eventually, all that gas gets coalesced and eventually starts a process of nuclear fusion where they eventually start fusing hydrogen to helium and then they start fusing heavier elements. And eventually, that's how a star's life begins. And eventually, most of them also start their own solar systems. As the star's luminosity increases and its gravity increases, and eventually blows out all of that dust from the outer to the outer parts of the solar system, and leaving behind materials of rock and dust, where it eventually starts forming rocky planets, and then all that gas coalesces become gas giants. And high mass stars do the same thing. They increase luminosity, their gravity increases, and eventually pushes out all the elements to the farther outer reaches of its star. So, now we're going to go to the next chapter. We're going to go to the actual future of these stars, and let's determine what's the difference between a low mass versus a high mass star. So now we're going to get to low mass stars, and this is actually a perfect example of the sun. So we're going to go to the star's life. So about 4.5 billion years ago, the sun was actually surrounded by a cloud of dust and gas, and eventually collapsed down to a disk where it formed the solar system. Now, how the star keeps alive is because it's fusing hydrogen to helium. And then over time, it bathes us with warmth and, gives us life on Earth. But like all things, must come to an end. So now we're going to go into the first billion, where the star's luminosity is going to increase a lot. And it's going to about getting bloated because it's already exhausting all that hydrogen and eventually forming into helium. So now, as time goes on, the next billions of years, now we're going to go into the 5 billion year journey right now. Star's luminosity increases. It's already big, bloated, red giants, and pretty much engulfing Mercury, Venus, and Earth. Because it's already big and bloated, and it's already 750 times larger than our current star right now. Because it's, like I said, it's exhausted all its hydrogen. Now it's helium, but now we're going to add into carbon. So once the star gets into carbon, its outer reaches and the core cannot take it anymore, where it's already pulsating. So it's contracting as the core gets smaller. So it's contracting and pushing the outer plasma out and continues to get deeper red as it pretty much pulsates and actually becomes another red giant. And it continues to push those outer layers so much where it becomes a fluorescent nebula. So now our sun's ultimate fate is an Earth-sized white cinder known as a white dwarf. So eventually, that white dwarf is not going to stay a white dwarf it's going to stay like that for billions of years, like hundreds of billions of years. And eventually cools down so much, becomes a brown dwarf, and then becomes a rocky world in the next trillions upon trillions upon trillions upon trillions of years. Actually, for the rest of the entire universe's life, it's going to be staying as a dead corpse, as it was. And that's pretty much the end of the sun. And like I said, all these low mass stars have that billion-year journey. Depends on the mass of these stars. Some of these are a little bit bigger, but they're still low mass stars. They're probably last about a billion. But if you look at that very tiny little red dwarfs, that can probably last about tens of billions. But our sun is directly right in the middle, where we're going to be called a yellow dwarf star. And these lifespans of these yellow dwarfs can only last about at least 10 billion. But these little red dwarfs can last a little bit longer than our sun because they're a lot smaller and they're cooler than our sun. So pretty much with all that, these little dead zombie-like stars are going to be lasting as long as the universe is going to keep expanding forever. So yeah, that's pretty much the difference between a low mass star.
So before we get to the new chapter of high mass stars, let's talk about where the sun is on its spectrum. So all stars are broken down in a spectrum based on their temperature. Red stars tend to be much cooler, whereas blue stars become much hotter temperatures. So where does the sun pretty much lie in that spectrum? Well, it lies about somewhere in the middle, being a yellow dwarf. But where is it in its life cycle? It is about over halfway of its lifespan, and it has another 5 billion years of life left.
So now let's get to the chapter of high mass stars. So these are very different stars, and they're much, much bigger than our sun. And they eventually, pretty much as they get so much bigger, and most stars started off as nebulas, but they draw in a lot more gas than low mass stars. But eventually, as soon as they're born, just like Mustangs, they burn through a lot of fuel very fast. They already burned out through their hydrogen, and then now they're now converting it to helium. And eventually they start fusing heavier elements as soon as they're born. And that's pretty much how a high mass star lives through its short lifespan, by fusing heavier and heavier elements. So high mass stars are very short-lived, depending on the size of the star. They can only live up to millions of years old, up to tens of millions of years old, just depending on just how massive these stars really are. Let's take, for example, Betelgeuse, located about 642 light years in the Orion constellation, located about the shoulder of the Orion. And eventually, as soon as Betelgeuse lives through its lifespan, it only has 100,000 years of its lifespan of life, because it's already fusing towards iron and going through the periodic table of elements. Now, once it gets to iron in its core, now the star only has 1 second of life left. And eventually, the core cannot take it so much where also the outer layers will eventually explode and becomes a supernova. Where actually it's so visible that it's so bright that actually it's visible from the naked eye, where actually it outrivals the full moon up to 2 weeks. So now let's take, for example, another high mass star. Let's take UY Scuti, the largest known star in the universe. Once that fuses to iron, it has 1 second of life left. Eventually becomes a massive supernova that eventually its outer layers form a massive nebula, almost like the pillars of creation. It was formed due to a very big star from the early parts of the universe. And the pillars of creation are probably around 10 to 13 billion years of age. So because it was formed by a high mass star that pretty much, went through its life and eventually became a big old supernova. So that's the fate of UY Scuti. As it pretty much fuses iron, 1 second of life becomes a supernova. But now this is where it becomes the ultimate fate. See, now it's already a white dwarf star, but the inward force of gravity contracts the core so much, it becomes much denser. Eventually, when it gets to 20 to 30 solar masses, and eventually the core will contract so much where it becomes a black hole, where the gravity is so strong that not even light can get out of a black hole. And eventually, because of a black hole where it just rips through anything. So pretty much also lower high mass stars can also form into pulsars. These are rapid rotating stars. These are dead zombie stars that shoot out these electromagnetic radiation jets that can span up to billions of light years. Eventually, these electromagnetic radiation jets are so strong that they can rip through anything at a near instant, where it can actually rip through an atom. That's how strong these electromagnetic jet beams are. Crazy, right? So our sun will not eventually do that fate because it's not massive enough. So thank you guys so much for watching this video by learning about the difference between a low mass versus a high mass star and pretty much their lifespans. So their lifespans are totally different. So a low mass star can live up to billions of years old, eventually becomes a red giant, becomes a white dwarf, whereas that cinder, that ultimate fate, slowly cools down. See, a high mass star, the ultimate fate is a white dwarf that's slowly pretty much getting dominated by that inward force of gravity. Eventually, most massive stars form a black hole because the inward force of gravity crushes them so much that the gravity is so strong that not even light can pretty much get out. So that's pretty much what you guys learned. Also, if you guys want to learn more about space, give me some questions about the cosmos if you guys are wondering. I do have a community tab where you guys can post those questions. And yeah, subscribe to the channel if you guys are brand new. We're on the road to 2,000 subscribers. So this is my 1,500 subscriber special, learning about low mass stars versus the high mass stars. And this is, something I want to learn about on this video. So yeah, subscribe to the channel if you guys are brand new. Send me some questions. And as always, keep exploring.